So the central limit theorem tells me for a mean that if I know that I'm taking any population and I'm sampling from it, as the sample size increases, we get closer and closer to a normal distribution. And that normal distribution has as its standard deviation of the original population divided by the square root of the sample size. Now, page 278, as well as the video I linked to on Friday from 3 Blue 1 Brown, says that it absolutely doesn't matter what distribution you start with. Whether it's uniform, normal, or something else, as we get a larger sample, we get to a bell curve. And we'd actually see how this is affected by our sample size from here. Clearly, these are not normal distributions to start with. If I take a sample of 1, well, it doesn't look much better. But as I take a sample of 2 and then 4 and then 8 and then 16, we get things that look more and more like a standard bell curve, with the mean here being in roughly the same place as the mean in the original, and a narrowing standard deviation, a narrowing spread. Questions? Normally, we make an assumption that I need a sample size of 30 or higher to get to the point where I can say I expect to be getting a normal distribution for the sample mean. If I have less than 30, I'll need to be able to adjust what I'm really looking at. It won't truly look like a normal distribution, so I'll need to fake it a little. But a rule of thumb is that if I have a sample size bigger than or equal to 30, yes, it's good enough to assume that my mean has a normal distribution. And that means that I can nail down a range. So, working with the data from the GMAT exam that we were talking about on Friday, the graduate exam in management, I can decide, all right, how precise do I want to be? I can make a choice and say, I want to be this sure that my range is, my sample average should be in here. And how we decide that is to give a lower bound based on the z-score that goes with how precise we want to be. Now this, upon first example, doesn't make very much sense. This is about as clear as mud. When we were talking about z-scores, we were able to talk about the highest so much percent, the lowest so much percent, or the middle so much percent. Okay, hang on a second. If I want to be 90% sure that I'm using the right interval, then I should find the z-value so that this covers 90% of my normal distribution. All right, hang on a second. If I want the middle 90%, there's a bar at the bottom that cuts some off. There's a bar at the top that cuts some off. Draw the picture of the normal distribution. There's a bar there and there's a bar there. And I want the middle to be 90%. If I want the middle to be 90%, what are the z-values that make up these lines? I don't have to know them by heart. I have to be able to get them. How do I figure out what z-value this is?
1 minus the 90.9.
So that would be 10%, right?
10 divided by 2 for 1 for each side.
Which means I need this area here to be 5%. So I can look up on my table an area of 5%. I can do that off of table C2. I can do that on here. Find me a z-value that goes with an area of 5%. I don't care whether you do it off the table or off your calculator or off of Excel. You can do it in lots of different ways. As a matter of fact, it almost exactly splits the difference here between 164 and 165. So normally, we split the difference and write it 1.645. And that's the low one because that's the area being 5%. But this area is also 5%. So by symmetry, This is positive 1.645. That's the number I'm going to use here in this range in our interval for z. Let me go back to that exam data that we had at the start of class on Friday, where I had an average and a standard deviation that were known. And we were taking samples that were how big when we did this problem on Friday? Y'all were here. You took notes. You heard me talk about it. Page 274. We took samples of size 5. That's my n. So the the standard error of the mean is 86.80 divided by the square root of 5. Grab your calculators, give me a number. Give me one more decimal place. That way I'm at 2 decimal places for everything. So now what I can say is that the interval should be 520.78 minus 1.645 times 38.82, comma, 520.78 plus 1.645 times 38.82. This is the interval now back to the x scores rather than the z scores. If we used 1.645 for the boundaries, that would be the z boundary. But I'm going back to the setting for the exam scores, so it's the same idea. We've just moved back to the exams. This is an interval for x. X bar should be in here. There is a mathematical symbol that means is in something. It looks like a funky lowercase epsilon. I'm not going to use that notation very often, but I thought I'd mention to you here. And you can give me 2 actual numbers here. I get, depending on how you round, 456.92 or 93, and then 584.64. Same idea. So if I take a sample of size 5 from the hundreds, thousands of students, I'd be able to tell you this is where 90% of the time I should be in here. Now, what if I don't just want to be 90% certain that I got the right interval? I want to be 95% certain or 99% certain. If I want to increase my level of certainty, what should happen to my interval? Bigger. It should get bigger, which means my z values need to get bigger. And if we think about it, that's because the area in the middle will get bigger. From 90 to 95, those 2 z's should move out. From 90 to 99, they should move out further. As a matter of fact, I should be able to do the same idea for 95%, but what's my little corner area if I'm doing a 95% in the middle? And if I remember correctly, on our table, 2.5% is in the box. As a matter of fact, 2.5% for the low end. Wrong table. 47.5%. Wait a minute. Why is it 47, not 97? Because this is table C1 and it's only working on the half of the screen. But there we go. That number, where the box is 1.96. If I want to be 99% sure, how much should be in each little tail? 0.5%. So that's 0.005 or 0.495, right? 495. There we go. 2.57? Between 7 and 8. So I can actually keep these numbers in mind. Now, I can also get these numbers without using the table if I use Excel or I use my calculator, because on the calculator, these come from taking the normal inverse setup. So the calculator command is inverse normal, which is hidden under our distribution menu. And then I can put in what area I want. If I want 5% in the tail, I put 0.5. If I want 1% in the tail, lo and behold, oh wait, we wanted 0.5% in the tail. Let's change that from 0.1 to 0.005. There we go, 2.576. Now they gave me the -1 because I was looking at the left edge. You want to look at the right edge, you have to take 1 minus 0.005. But in either case, I'm using plus here and minus here, so I'm going to use the same number in the positive and negative version. Questions? Yes, ma'am.
You were saying that we have access to the charts whenever we take the exam.
Oh, yes, you'll get exactly a full copy of Appendix A and Appendix C, both part 1 and 2. They're printed out, you'll be handed them. I don't expect everybody to master all the calculator intricacies in the next 48 hours. That's unreasonable. Even though I did put up the manual pages on Canvas, which is so accessible right now, we can still do it without this. Questions? This assumes we know information about the population and are then trying to predict what happens when we take a sample. That's not usually the case. Usually, we don't know about the whole population. We only know about the sample. So I want to take this same idea and reverse the roles of X bar and mu. So rather than using my known population behavior, I'm going to use what I know about the sample. And we're going to call this a confidence interval. Now, there are two different kinds of confidence intervals, and it depends on what we know about the standard deviation. I'm going to start where I know the population standard deviation, sigma. Now, why would I be in a position where I would know the standard deviation, but not know the mean for the whole population? Well, it could be that I'm looking at a process like an assembly line or a manufacturing facility where the variability is known, but the exact average isn't. So that's actually something that we can determine out of process. But the sample mean X bar is the estimator. Mu is the parameter. So I'm going to try and create a confidence interval, and that means I need to give or take a margin of error. And again, that margin of error is decided upon by our desired level of confidence. So I want to be 90% sure that the real parameter for the average is in my interval. Or I want to be 95% sure, 99% sure, 98% sure, however I want to do this. Alpha is 1 minus the confidence level. So alpha is a small number. So if I said I want it to be 90% confident, then I'm saying that alpha is 0.1. If I want to be 95% confident, then alpha is 0.05. 99% confident, then alpha is 0.01. I get my margin of error by doing the same thing we just did. I find the z level for the tail, and I add or subtract that much times my standard deviation. Now, before I lose my mind, somebody tell me, why did I write alpha over 2?
You're dividing it in half, what is for each side of the tail?
One side of the tail is down here on the low end, one side of the tail is up here on the high end. The tail is this big in area, but that has to be split into 2 pieces. Now, the best part is that means we already know the three most commonly used numbers for Z that we're going to use. The ones that go with these three confidence levels. That confidence level of 90% means that there's 10% of the area out in the tails, means 5% down to the bottom and 5% up the top. What was the Z value that went with that?
One point six.
4.5. And I'm writing Z.05 because that's half of the alpha. Here, Z.025 is 1.96. And here, Z.005 is 2.576. Exactly the same numbers we were just working with. And again, if I want to use something different, if I'm not using 90, 95, 99, say I'm using 98%, well, then I could use Z of 0.01, and I can look that up on my table. I can generate that Z value directly. What the hell does this mean? Page 282. I go out and I take my sample and I get the average. And I can now say I am 1 minus alpha, confident, 90%, 95%, 99%. That the mean for the whole population is inside this interval based on my sample. There's only an alpha chance that it's way smaller than that or way bigger than that. I'm confidence level sure it's in the right numbers in here. That's a really useful statement. I do a sample of heights on campus, and I get 5'7" from 12 people. And I want to be 90% confident. The standard deviation is 3 inches. So I start working this out with 12 people. What's the size of my interval to be 90% confident, 95% confident? The right height is between 5'4" and 5'10". Oh, I want to be 95% confident. I got to go out further. I have to go out to 1.96. That would be almost 6 inches. So down to 5'1", up to 6'1". I'd get a larger interval, right? I'm 90%. I did a survey, I got 5'7". The right answer should be between here and here. I'm sure of that. The larger my sample, the smaller the standard deviation gets, the smaller my confidence interval gets. So small samples give me big confidence intervals, big samples give me small confidence intervals. You've seen this in graphs of data from lab classes, right? You get this is the number we computed, and then you get an error bar above and below it. That error bar is based on this margin of error. I'm never going to be 100% sure. It's not possible. Until I actually survey the entire population and I'm 100% sure I got the whole population, which is, really likely. Most of the time, I can't assume a normal sample, a normal population, or a normal distribution. until my sample size is big. And to me, big enough is 30. Otherwise, I need a larger sample. And if I have a smaller sample, I'm going to be in trouble. Quality assurance or manufacturing behaviors give me known processes where standard deviation can be known. Problem number 13. A random sample of 25 items is drawn from a population whose standard deviation is known to be 40, and the sample mean is 270. I want a 95% confidence interval. Sample of 25 items is taken, and the standard deviation for the population is known to be 40. The sample mean is 270. I'm going to use CI as shorthand for confidence interval. I want a 95% confidence interval. Where do I start? Yes, Phyllis. Okay, at 95%, what's the z-score I need? Exactly. Now that's z of 0.025. Remember, it's z alpha over 2. Half of 0.5, 95% interval. Alpha is 0.05, so that's alpha over 2. Now, I need to do the standard deviation divided by the square root of n. So it's 270 minus 1.96 times the standard deviation divided by the square root of n, and then 270 plus 1.96 standard deviation divided by the square root of n. This is my confidence interval. Give me a number. Give me at least 2 decimal places on each calculation, but give me a numbers. Fortunately for me, square root of 25 is 5. 40 divided by 5 is 8. That's a nice number. So this becomes 8, and I take 1.96 times 8, subtract it, and add it. So, what does this set of numbers mean? Felix?
95%.
Assurances or
Yeah.
confidence.
Confidence that our mean of motivation lies within the.
I'm 95% sure that the right answer for what is the average over the whole group is in there. Now, 25 is not a big population. So what if I increased the population? If I did a sample instead of doing 25, what if I did 50 or 100? A larger sample would give me more confidence in my result, but what would that do to my interval? It would make it narrower because this denominator would get bigger. When the denominator gets bigger, the fraction gets smaller. So if I switch to doing the same idea with n equals 50, then I'm going to get a smaller number there. My margin of error gets smaller. Now this time, the square root of 50 is not a nice number. So I'll just leave it as the square root of 50. And when I go to do the subtraction, I'll type it in exactly that way. 1.96 times 40 divided by the square root of 50. And when I subtract, I get this number. And then I can repeat the calculation and change this minus sign to a plus and get the other end. So now my interval goes 258.9 to 281.1. So notice what's happened is that my interval got smaller because the larger my sample size, the narrower my margin of error gets. In a sense, yes, Felix, I am more confident that I got the right answer with my sample because I did a bigger sample. I'm more sure that this is the right answer, so I can narrow the interval. If we went up to 100, it would be narrower still. I will point out to you the two actual settings for examples in this section. 815 talks about fuel economy, and 17 talks about we're making cans, and the process has a known standard deviation of the thickness of the metal they use for the can as it's drawn into the right shape. This one is talking about ages at a ski mountain, and they make an assumption about the standard deviation there. I'm not sure I can make that assumption out of a normal population without some extensive background data. I'd be hesitant on that one, but these two, as processes, I'm pretty sure I can get more information about the standard deviation. Questions? Another note. Under the statistics menu, which is where we did all of our descriptive statistics, we had lists that we could enter, and then we could do the descriptive statistics here, and it calculated them with this one variable statistics here. Well, there's another column over there on the right that says tests. And we haven't done anything about testing yet. What we have done is about an interval. Look at the bottom of this screen. it says Z interval. As a matter of fact, if I go down to that option number 7, and I say, I want to get a Z interval, it's going to ask me, do you want to give me data or do you want to give me the statistics? I want to give the statistics. The problem we were just doing, this one right here, had a standard deviation of 40 and an average of 270. And we were getting 50 people. And we wanted how confident do we want to be? What was the confidence interval we just did? So I want to be 0.95 confident. Now remember, the calculator can do z-values. It can look up the z-value for a known area. That's what the inverse thing does. So it's going to do that automatically for me. 258.91, 281.09. That's the same interval we got here, except for my copy error, because that should be an 8. I don't have to look up a damn thing. If I know how to use the technology, I can automate this in Excel the same way. Yeah, 258.91. I wrote it down wrong. So under stat, under tests, that Z interval section will do this sort of confidence interval for me. Yes, ma'am.
Both of them, so I know I have the 280 on it.
As soon as I told it to calculate, it gave me them both. Do you have a left, right, center thing again? If they've updated the software, I don't know. All I can tell you is what happens when I push the buttons. This is why I like having the tech, but I don't like relying on it. Now, the problem we've already come up with is the fact that I said knowing the population standard deviation isn't common. So what if I don't know sigma? If I don't know the standard deviation for the population, I can't just guess. What happens is that I actually need a different distribution. I need something that looks kind of like normal, but isn't really, because I'm not making any assumptions about the populations. So it could be bigger, or it could, wait a minute, we did this already once, didn't we? We talked about the difference between a population standard deviation and a sample standard deviation. A little bit of history and beer. W.S. Gossett was working for Guinness, the brewery in Ireland, and was working on yeast strains and yield in terms of the alcohol they produced. But he didn't have a lot of samples. So he knew he could not create a normal distribution from 3 samples and started to look at a normal distribution and fudged it a little. He lowered the peak and spread out the tails to be bigger. And Gossett said this makes up for not knowing the standard deviation of all the yeast results. I can make do. Unfortunately, Guinness was really, really, really picky about letting their data out into the world. And so Gossett wasn't allowed to publish his studies under his own name. As a matter of fact, anybody who did work with Guinness's data was only allowed to publish anonymously as student. And so Gossett created a new PDF, a probability distribution called the student's t-distribution. And it has an additional parameter. Which Gossett called degrees of freedom. Abbreviated DF. And fortunately for us, degrees of freedom is fairly simple. It's the sample size, take away 1. The t-distribution kind of looks like a normal distribution. It varies based on the number of people in the sample. Page 286. Here are 3 different curves. The darker one is the standard normal distribution. The red, lighter one in this picture is the student t-distribution. Notice the peak on the t-distribution is lower, and the tails are higher. Gossett said, if I don't know the standard deviation, there's a bigger chance we could be out there because there's more weight possible. The standard deviation is what allows me to bring it all in. I don't know that. So I need to make the assumption that there's more weight out there. But as the number of people get bigger, the differences between the 2 curves get smaller. As my sample size gets larger and larger and larger, the t-distribution looks more and more and more like a normal distribution. I guarantee you, you will never be asked for this information ever again, but it is possible to write the formulas for these distributions. That's disgusting. I don't want to do it. Not only can we do the PDF, and the CDF, I'm not going to do this. This is gross. And then I need to do integrals under these things to find the areas under the curves. Oh, joy. No. Not just no, hell no. The best part about this is that all I need to do is look up a new table. Gossett spent years doing practical experiments and calculus to get another table. And in Appendix D, you will find a student T table. And it just lists critical values. These are the numbers we're going to use based on our confidence idea. So I'm going to recreate confidence intervals. Well, instead of using Z values, I'm going to use T values. But that is what is going to happen on Friday. Because on Wednesday, we have the exam. I will post at home the review sheet key and the homework key as soon as Canvas comes back up. But if it hasn't come back up by the time I get done with my meeting at 6 o'clock, I will email you all of those files. If you have questions, please come to my office hours tomorrow. Please email me. I will see you all on Wednesday. Have a wonderful day.